Let V be the vector space under the usual operations of real polynomials that are of degree at most 3. Let W be the subspace of all polynomials P of x in V, such that P of 0 is equal to P of 1 is equal to P of negative 1 is equal to 0. Then the dimension of V plus the dimension of W is 4, 5, 6, 7, or 8. Okay, so my quick intuition here is to treat every constraint that we're given as a reduction of the dimension by 1. I'm not sure if that's even correct, but intuitively it kind of seems like it should be correct. So the original vector space D, polynomials of degree at most 3, that has dimension 4. So an arbitrary polynomial of degree 3 can be written like this. We see that we have 4 degrees of freedom here. In fact, these polynomials, including the constant 1 here, those are a basis for V, and there's 4 of them. So we see the dimension is 4. And now, if we impose, for example, if we impose only the first, let me write out the 4 constraints that we're given here. I'll write them out individually. Like this. If we impose, for example, only the first condition and ignore those ones, then this is equivalent to saying that A0 is equal to 0. And so clearly we've reduced the dimension by 1. If we wrote out what this means, P of 1 equals 0, if I substitute x equals 1 here and say that that's equal to 0, that'll just give us a relation that the 4 coefficients have to satisfy. And then if we do the same thing for negative 1, that'll give us another relation they have to satisfy. And so each of these relations is reducing the dimension by 1. It's reducing the number of degrees of freedom by 1. The only catch here could be if, for some reason, one of these conditions is redundant, but that's not going to be the case. So in fact, if I look at this, then all of the polynomials now have to be of this form. Okay. If P of 1 equals 0, this means that A3 plus A2 plus A1 has to equal 0. And this tells me, in fact, let me write this instead. Instead of that, I'll write it as A0 must equal 0. And P of negative 1 equals 0 says that negative A3 plus A2 minus A1 is equal to 0. So, our collection of vectors which determine the coefficients now look like this. It's A0, A1, A2, and A3, where these conditions have to be satisfied. So we've reduced, the original dimension is 4. We reduce it by 1, 2, 3. So the dimension of W is equal to 1. And so the sum of the dimensions, which is what we're asked for, is 5. Yeah. So there were 2 key things I think that went into this one. The first is that the vector space of polynomials of degree 3, or at most 3, that's actually, that as a vector space has dimension 4, not 3. And that can be seen from here. And then also, when you have a linear space like this, every time you introduce a single constraint, you reduce the number of dimensions or the number of degrees of freedom by 1. And so by introducing 3 constraints, we've reduced the dimension 3 times. And so, yeah, anyway, this is what we get. If I have more to say about this one, I'll put it down in the description. Thanks for watching.